Now, imagine the immense physics at play when a train is just thundering down the tracks. We're talking about thousands of tons of metal moving at incredibly high speeds. I mean, it's essentially the equivalent of trying to stop a herd of 200 elephants sprinting all at once. So how exactly do you stop a machine like that on a dime? Well, it's definitely not like slamming the brakes on your bicycle. The sheer momentum involved means you literally can't just react to what you see. You have to mathematically predict it. To safely manage these absolute titans of the track, modern digital control systems must intimately, perfectly know the physical body of the train they're directing. Welcome to today's Explainer. We are going to unpack the fascinating, totally hidden mechanisms that keep our railway system safe and efficient. We're exploring the precise interfaces with rolling stock. This is that critical sweet spot where highly sophisticated digital control networks sync up perfectly with the massive physical reality of the trains themselves. All right, here's our agenda for today. We'll be covering Section 1, the physics of stopping. Section 2, braking characteristics and ATP. Section 3, train-borne equipment. And finally, Section 4, dimensions and overhang. Let's dive right into Section 1, the physics of stopping. You know, a train driver is constantly making split-second judgments. But because of the train's colossal mass, human eyesight simply isn't enough. The stopping distance of a train is vastly, vastly longer than a car's. That sheer momentum requires incredibly precise, data-driven braking models. And oh man, it gets exponentially more complicated when you factor in terrain. Just think about gradients for a second. If a train is traveling downhill, gravity aggressively grabs onto all that massive weight, drastically increasing the distance required to stop safely. Conversely, heading uphill shortens it. The entire control system has to account for this physical reality in real time. Moving right along to Section 2, braking characteristics and automatic train protection. So, what does ATP actually do? Well, automatic train protection is basically the ultimate digital safety net. It continuously evaluates the train's current speed against the distance to a speed restriction or maybe an upcoming red signal. If the system calculates that the train is traveling way too fast to brake in time, it doesn't just sound an alarm for the driver. It automatically intervenes and applies the brakes. It literally takes control to ensure the train stays within a rigorously, mathematically calculated, safe speed envelope. But, of course, not all trains are created equal, right? Take a heavy freight train, for example. Massive weight, slower speeds, and a tremendously long braking distance. Now compare that to a sleek, modern passenger train. Much lighter mass, higher speeds, and vastly better braking performance. Here's why this comparison is absolutely crucial. The physical spacing of the signals on the tracks themselves has to be designed to accommodate the worst-performing train on that route. The system basically has to guarantee that even the heaviest, poorest braking freight train has more than enough distance to safely come to a halt. If we look at how these signals are spaced out, the distance between the first caution signal and the actual danger signal at the end of the line isn't arbitrary at all. It represents the full service braking distance of the train, plus a really, really important S, a safety margin. This margin is often called an overlap. It's essentially a reserved section of track just in case there's inadequate deceleration. It acts as a physical buffer to prevent a catastrophic collision. Okay, let's jump into Section 3, Train-Borne Equipment Integration. Now, this is super interesting. We have two very different rail environments here. We've got a metro system using CBTC, or Communications-Based Train Control, and high-speed trains utilizing ETCS, the European Train Control System. While they serve totally different types of rail, both fundamentally require deep, continuous integration with the vehicle's onboard computers. They actually ditch traditional line-side signals entirely in favor of beaming digital movement authorities directly into a display right there in the driver's cab. To make those cab displays work flawlessly, the onboard brain is working overtime. The system is constantly crunching data: its current speed, absolute position, the distance to its authorized limit, its own specific braking characteristics, and that upcoming route gradient we talked about earlier. By calculating all these inputs together, the onboard computer achieves something kind of remarkable. It generates highly safe and highly energy-efficient braking curves in real time. But how does a train actually know exactly where it is in the world? It's all done through a continuous feedback loop. First, it reads physical tags placed on the track, called balises, to get a fixed, absolute location. Then, it uses odometry, literally counting the rotations of its wheels, to calculate the distance it's traveled since that tag. But here's the catch. The wheel-to-rail interface is tricky. Steel on steel has famously low adhesion. Throw some wet autumn leaves on the track, and wheels can easily slip when accelerating or slide when braking, which completely ruins the math. Actually, to get around this, high-integrity systems sometimes rely on a totally separate, unpowered, and unbraked axle purely to act as a highly accurate speed and distance sensor. It's brilliant. Finally, let's wrap things up with Section 4, Physical Dimensions and Overhang. So the really crucial concept here is spatial awareness. Think about a junction where tracks merge or diverge. The fouling point is this critical, completely invisible danger zone. It is the exact mathematical location where the outer edge, the absolute furthest extremity of a train standing on one track, would scrape against a train passing by on the adjacent track. The control system has to know exactly where this point is to prevent trains from sideswiping each other. Train detection systems, like axle counters, figure out where a train is by locating its wheels. But the body of a train always extends past its front and rear axles, right? This is known as the overhang. So, when engineers are placing track clearance equipment near a junction, they must specifically position those sensors to account for the physical body of the train extending out way past the wheels. And this, right here, is a massive takeaway to remember. The wheels are absolutely not the true end of the train. Because track-based equipment primarily detects the steel axles, the system's safety margins must intimately know the physical overhang of the specific rolling stock using that line. If the system only cleared the track based on the last wheel it detected, the overhanging tail of a train could easily still be fouling the junction, sitting directly in the path of oncoming traffic. And we definitely don't want that. We've gone from the raw physics of breaking hundreds of tons of steel all the way to onboard computers calculating real-time safety envelopes, and finally to the exact spatial geometry of a train's overhang. The control system doesn't just watch the train, it is deeply, fundamentally synced with the train's physical reality. It's a highly tuned mathematical relationship between heavy industry and pure digital precision. So next time you ride a train, staring out the window, ask yourself, what other invisible digital safety nets are anticipating your every move? Keep learning, and I'll catch you in the next explainer.